Welcome to today's webinar with the title Fast, Faster, High Speed, Physical PCB Sample WE.speed. I'm Andreas Schilp, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is a qualified specialist from Würth Elektronik Circuit Board Technology, Andreas Dreher from our Technical Project Management. Welcome back, Andreas. And now I wish you lots of fun and new information.
Thank you for your introduction and welcome also from my side. I'm looking forward to guide you through this very interesting and also complex topic. A brief introduction from my side. As mentioned, I'm Andreas Dreher. I'm in the CBT plant in Schopfheim, and my main focus are HDI design, signal integrity, and high speed, and a lot of affiliated topics around. You can reach me under the shown contact details and feel free to get me nice questions. Our agenda for today is the introduction to the high-speed topic to sort out what we are including, what is special, can we group some special applications. Main focus will be the features of our new high-speed sample, which gives you a chance to really get a touch to this complex topic. Also, we will go through what high-speed means for the PCB manufacturing, what special points are here during the production, and also of the planning of such a project. And very important, how to measure material properties with different measurement devices that we can use the values for improving the design. So let's jump right into it. As I mentioned, the topic is pretty big, pretty complex, and it is very fast, very detailed. So I try to group it as best as I can to give you a very good explanation in this short time we have here together. So I tried to group it into analog applications. Analog means everything with antennas, either big radar antennas for flight monitoring, for example, or also there are some small samples like an onboard antenna for a Bluetooth module or a wireless module. So again here, very wide bandwidth of different application. Another big topic and very fast growing are all about the digital applications, so high-speed data, everything which includes sensors, cameras, connection of memory modules, but even standard commodity links like a network connection or an USB plug or HDMI plug are in this category. And as I mentioned, they are very fast growing. So let's try to break it down. In the analog area, typically I have one target frequency, and the benefit of this is I can really fine-tune my my parameters and my design to this single frequency, or at least this array of frequencies. And typically I want to have controlled emission in the entire antenna area, or if it's in the receiving part, to receive things. So the signals are leaving the board. In the opposite to that, in the digital area, we want to have a good transfer through the board. The signals should go through the boards with as less loss as possible. And very often I have a frequency mix. Yeah? Imagine, for example, the computer in front of you. At the moment, he is only partially used up, it's not 100% of a bandwidth, so the frequency is lower. If you start gaming on your computer, it will be a higher frequency, and you have to tune everything from low speed to high speed on the same board, which makes things very interesting. If we break it down more, often the analog areas are low layer count, so sometimes a single or double-sided board is enough for antenna. If I combine the antenna with some digital ones, it gets more complex. The frequencies are a very wide range. Bluetooth is typical at 2.4 gigahertz. Motion detection or parking assistance are in this mid-frequency area between 6 and 24 gigahertz. And big radars are up to 80, 100, 120, and even higher frequencies, which maybe is a little bit out of focus today in this presentation. We will be a little bit below this. In the digital signal area, it's not always the frequency. It's also very important the rise time, which we discuss in the next slides. So often it's very hard to define fixed frequencies, but typical frequencies you show here, USB, depending on the generation, 2.5 to 5 gigahertz. PCI Express bus, it gets very fast, where we have to consider a lot of high-speed topics with such connections. So unfortunately, in this time frame, we cannot go for a full introduction that you can introduce me what your interest is, but I want to make a quick survey with you together and get a little bit of feeling what your interest is, if it's low frequency in this kilohertz, megahertz area, or is it in higher frequencies. And for that, I will hand over to Andreas, who can switch a survey, which we get a fast feedback from you.
Okay, here we are. I start the poll, and you should see a blue screen with 5 possible answers. Please choose one of them. So what maximum frequency do your PCB design requires? There's a S missing. Or does your would be correct, I think. Up to 400 megahertz, up to 1 gigahertz, and so on. Or last answer, more than 6 gigahertz. We are actually participation rate of nearly 70% already. That's interesting. So we'll have another few seconds waiting for your answers. So actually stable, over 70% participation, and I will now close the poll and show the results. So this is what you have chosen. 4% means up to 400 megahertz, so that's really less. 12% up to 1 gigahertz, 16% up to 2.4 gigahertz, 44%, that's the most, up to 6 gigahertz, and 24% more than 6 gigahertz. So that's interesting, and with these figures, I give back to Andreas, who will continue his presentation.
So thank you for that feedback. And I see we have a lot of experts already here in the topic, so we can really deep dive into this topic. And if you have any questions, feel free to use the chat function. So often the question is, where does standard materials are okay, where I need special high-speed materials, what is low speed, what is high speed, where is the sharp border. And unfortunately, there is no clear black and white answer to that. I really invested a lot of time to find a good answer for this very important question. And I learned, unfortunately, the clear answer is it depends. It depends on several factors, and I try to go with you for a few basic things. With this symbol, I try to differentiate. We have the radar parabol antenna for analog sections, and this means high-speed data transfer rates. So that's more for the digital applications. So often the signal propagation time is very critical for differentiate when I have to use high-speed rules and even high-speed materials. Let's try an easy example. I send here from my component to this differential track a signal, and if my signal travels through the board, I have a signal layer on top, a ground layer underneath. There will be a condensator effect, and the condensator have to charge up, and a little bit of current is flowing back to the circuit. And the signal propagates through the material. It starts really like a wave. Imagine a water wave in a small channel. You empty a bucket of water in one side, and the wave of water will travel through the channel step by step. And that's the idea, what happens here. And if my length of a track is longer than the travel time through the material, which has a speed of 50 centimeters per picosecond in FR4 material, then definitely you have to think in such a wave propagation, and the high-speed rules will apply. It's a simplification, but let's start here. We have two things. The rise time of a signal defines how fast we get this charge up, and then it defines later the frequency. And as longer the track is, as more signal loss we will have. And if the signal is too weak at the end, I only get a noise, and I couldn't decide which was a 0 or a 1. So I have to take these parameters in consideration, and that's defined by components and also by the setup. If I have, for example, connectors in this path, I have vias in this path. So a rule of thumb, a general rule of thumb is test your design if you exceed 3 gigahertz or have rise times lower than 10 picoseconds. This is a general rule. If you didn't consider high-speed design parameters, then you should at least use this as a trigger and think about what is happening on your application. From our perspective, we can have an influence to the material parameters. I think everybody knows the good old FR4 material, which we are using since several decades, typical epoxy resin systems in different TG values. Typically the DK and DF is around 4 point something at 1 gigahertz, and we can have filler inside the material with or without, depending on the material. Yeah, that's pretty often used for comparison. Some other materials, for example, the Panasonic Magnetron 6. Here we modified, or the supplier modified the material to a lower decay, and very important, a lower loss. Yeah, you can see here it's 1 decade better, low loss material at higher frequencies. So that's very important. And he achieved this by changing the resin. It's really a completely new material. It's not an epoxy anymore. It's this PPE plastic. And you can modify the parameters with some fillers, including to the material. Another comparison or example is the Rogers material. There we have a hydrocarbon basis, that they are pretty top secret, what really is inside the material. And also they have ceramic fillers, which make this typical white color of the material. The parameters are pretty in the same range as the Mectron 6, but has a very high TG value. So that's how the material can modify it by completely changing to another plastic style and adding special fillers to change the high frequency properties. What does this mean in the PCB production? First of all, when we buy the raw material is more expensive, and the price increase as TG150 material as a baseline is ×4 up to ×20. So very fast the material gets very expensive. Due to the changed materials, we have to use more aggressive chemistry to achieve, for example, a good desmearing, that the adhesion of a copper is better. So this needs more effort. Due to the high TG values, the multi-layer pressing needs higher temperature and more time to get a good curing of a material, that the material gets his final properties. And drilling, due to the filler material, is more difficult. As you know from our previous webinars about costs, there's a nice comparison how long you can use a drill bit. For example, a typical drill bit has a lifetime of 3,000 hits, 3,000 holes. And if you add, for example, these ceramic fillers, the lifetime will decrease 10 times. So in Rogers material, you can only drill 300 holes, and then you have to change the drill bit, which adds a lot of time and also money for the additional drill bits. So there are important changes in the production of these high-speed boards. So it's very important to have a good qualification of this material, that all these changes are very well understood and implemented in new parameters. And we have now qualified the Panasonic Mectron 6 for also complex HDI structures, and also in combination with some flex materials for flexible boards. For special applications, we have a Rogers 4000 material available, which is very fast, very expensive. So there is a big consideration point if you have to use these special materials. If you need other materials, we can go with the Asia production team and look through global sourcing if we find a partner which can provide this material. But these materials are available in Germany, in the German plants. So let's jump in to the physical sample, the high-speed sample, where we try to implement as much features that you really can get in touch with this technology and get a feeling for it. If you want your personal sample, you can order them now. You can either use the QR code or get this link and order your sample via a small form, and you will get it in the next weeks. If we have a close overview, we have tried to divide it into some analog applications, some filters. We go through it step by step. We have some digital applications on the backside and a measurement coupon to measure the material parameters. But let's go through it step by step. First, a look inside of the material. We created a stack up with a lot of different impedance values. So we have all the impedance tracks on the outer layer, on layer 1, The ground is layer 2. We have created 50 ohms, 90 ohm differential and 100 ohm differential with the shown parameters, which are very typical in use. You cannot copy and paste these parameters into your design. It has to be fixed to the material and also the stack up. So if you want to use some impedance controlled stack ups, feel free to ask us for your individual stack up. We created with our background in mind that we really can also produce this very stable. And again, if you are knowing Würth Elektronik for some years, you know we can create you the impedance calculation, helps you by material selection, the design rules, and also we include the process tolerances that we really can produce this board stable. If you need more on top, you can order the impedance measurement, that every panel in the production gets measured on your critical signals, and this is helping us very good to achieving a process control. And we will have a focus on a new measurement device, the Atlas measurement system, which can create a very good understanding also for high frequencies, but more on that later. So if we have a look on the high-speed area of the hand sample, of the physical samples, we have here included a pattern with a zigzag routing. What it is for, you ask? Yeah, there is a so-called fiber weave effect in the board. If you have two tracks, a differential pair, for example, on the material, you see here underlaying the glass fibers of a 106 prepreg style. And if by chance one track is exactly on top of this glass fiber and the differential pair next to it is in the gaps in between, it will see a different decay value, and the speed of the signal changes. So you get skew in the parameters, so the signal will not come at the end at the same time. This can be changed either by using different prepreg styles or by design. If you use this zigzag routing, you get a mix of all different material, and this effect here is minimized. This was used in a real application. We have a so-called WE design team where we can offer you to create or modify your existing designs. You can come to us with a list of components and a net list, and we create you the design, and also can provide you, of course, the PCB from our production plans. That was done here, and due to this frequency mix, and it was very important that the signals reach at the same time, this zigzag routing was implemented. Another thing you see more and more on high-speed boards is the so-called snake routing. What is snake routing? If you want to have differential pair through the VGA area, you can use, if your software supports it, you can use the snake routing. The feature is you have no sharp corners in the design. It's beneficial for differential pairs. The tracks are better together and are more stable. And sometimes you can improve the spacing in the design, especially in this diagonal grids in BGA areas. It's more a soft fact. The big point is, can your software support it? Drawing something like this by hand is very tedious and not recommended. The really upgrade in the software is possible. In the left-hand side, we have a representation of an HDI design. and it shows that also with this material, complex stack-ups are possible. All typical HDI designs and technologies is also available with this new material. And often there is a task that you want to have a signal from a top layer, for example, to the layer 3, and you don't want to have this stub, so-called stub here in this area. This is on one hand side an antenna for external signal or for crosstalk, that other signals are fed in to this network and destroy the clear signal, or you have reflections of your signal through this board. So what was done in the past is using backdrilling and destroy part of this whole wall, also here seen in the cross section, to get a small stub as possible. Maybe you know from your homeworking that if you try to drill a hole in the wall to hang up a picture with an existing hole with a bigger drill bit, it is very difficult to make a good, nice hole. Same thing here in the PCB. So it is not always possible. It needs a lot of space. You need a lot of clearance. You see here the small vias need a big drill bit to get rid of the material. So here a HDI approach is sometimes beneficial. It has a smaller footprint. You can route the signals very fast, and it's more reliable than back drilling. Also, an additional point, if you have already microvias present in your design, if you add more microvias, it will not increase the costs as much as you, for example, use a lot of through holes. So if you have already microvias present in your design, you can use them as stitching vias to shield your signal lines. If we flip the samples over on the other side, we have a mixed section. So it's a mix of an analog and digital signal. We have a BGA, which have an antenna grid for sending and receiving data. The chip is evaluating the signals and providing it as a digital signal to the rest of the circuit. In such applications, it is very, very important to define the critical impedance tracks. Often here, very tight tolerances in size are needed. And for us, it's often very hard to find out where the critical path is and what is the standard track. The point here is the standard IPC tolerances are often too wide for such an application, and if we just apply the standard tolerance, the performance of the system is not as good as expected. So how to define this track? With the improvement of IPC data format and the new Gerber formats, there's a possibility to get attributes to this nets. If your software is not supporting this, a very simple trick is just add an increment to it. The standard layout, just as a random number, is 150 microns, and the impedance track is 150.1. So it's very simple, very fast in all CAM tools to identify where the critical tracks is. To the effect on the tolerance, as higher the copper is, as more tolerance you have. If you have a big via array, so if you have a VGA with a lot of through holes, if you fiddle a track through this area, due to the different flooding in our chemistry process, the etching parameters are different and the size will change. And if you combine different technology on this layer, for example, via type 7 with filling and capping it and through holes in the same process, is two galvanic processes are needed, and if you add more processes, also the tolerance will increase with every additional tolerance. So opposite is to decrease the tolerance. As lower copper is, as lower the tolerance will be, and as homogeneous your layout is, we always like copper flooding, add as much copper as possible. As more homogeneous it is, as lower the tolerance will be. In the filters and antenna part, there are just some typical values. I don't want to dive into this topic too deep because, to be honest, I'm not an antenna expert. But there are a lot of simulation tools to calculate such structures. But I know from our processes to fine-tune these areas. Again, definition if critical. If we don't know what you expect, it's very hard for us to fulfill the expectation. So how to define these structures. Sometimes design in is necessary. What this means, I show you on the next slide. And also a definition of a quality control is useful because, again, the IPC tolerances are often too big for that kind of structures. We can fine-tune it, but that has to be defined how we do it because it's also more effort. So what does design in mean? Here, a task was to create a square pad 100 by 100 micron. And in the CAM software, it's very easy. You just draw a rectangle. You have perfectly 90-degree angles, sharp corners. And what we will see in the real life, something like this. It's more like a potato, not like a rectangle. So that's without etching optimization, which we typically do. But if we know that this pad is critical, such a structure, we can really optimize to get as close as possible to your target as needed. Also, other example, the target was to have line and space with 30 microns line width and 50 micron space. It has a dedicated test pattern. And you see here in the middle area, we actually pretty close got to this target. But as on the outer areas, the target was not 100% reached. Why, do you ask? If you look into the machine, this is a typical etching machine. You have these spraying nozzles all over it. You spray the chemistry on top, and you can imagine here in this area, the etching solution can flow left and right, but here you have more turbulent flow, and as more turbulent it is, as more etching you have. This is line specific. So in the etching line, we know these values, we can fine tune it, we can modify the track beforehand, but we really get very close to the target. But again, we need to know what your target, what your expectation is. And therefore, some discussion about this topic is needed before we start production. Okay, also in this area, Michael Mattes, the designer of this sample, was created and wants to get you some nice ideas for typical connectors. So, for example, this connector here, it was done by first of depth milling in the drilling area before the galvanic. In the galvanic, we did an edge metallization, so the edge of this is fully metallized and provides a very good shielding. If you need a shielding for this structure, and in the etching process, it is finalized. It's a fictional connector. There is no real component to it. You just want to start your creativity also with this drilling. Maybe it is a possible connection for a waveguide. So just be creative, and if you have very special needs, feel free to ask us how we can achieve this target. A big part of the coupon is also this delta L 4.0 measurement coupons. we are the first PCB supplier in Europe which is capable of measuring the high-speed values in our facility. So 2 doors here from our webinar office is the measurement unit, the Atlas device. It's a vector network analyzer with good software which can create you a lot of scattering parameters, the dissipation factor, or the effective dielectric constant of the materials. And that's the important thing, up to 40 gigahertz. Let's have a closer look to it. So very often the problem is, if you know your measurement device, you can calibrate your connectors, your cables to the plug, but the probe itself, and especially the PCB connection and the vias in the board, you cannot calibrate very easily, or sometimes even it's impossible. So what the Intel guys invented with this measurement device, you measure 2 different lines, can be a 5-inch and a 2-inch structure, or a 10-inch and a 5-inch. And then you calibrate out all the connections, all the probing, and you just measure the middle area, the area of interest. And here I have some examples what the software looks like. So you can have here the S parameters in that kind over a low frequency up to 40 gigahertz, the transmission loss through this track, a lot of other parameters, and often for us very important is the effective epsilon air. So here a close-up. You can see here again the effective epsilon air around 3 point something. And important is, or interesting is, that in the low frequency area up to 1 gigahertz, the changes very drastically, and afterwards it's more stable over a wide range of frequencies. And so that's very interesting and very important to really measure, not only use the datasheet value where you only get some numbers, really get an idea, an impression of a real physical example. So pretty good measurement system for the delta measurement. And if you want to have some measurements, we can of course measure it on our boards or on our test coupons, but also if you have external coupons from other interesting areas, we can offer you a measurement service on this system. So let's sum up all these interesting things. I think everybody knows this graph about the effort during the project phase. Yeah, you have the early phases, which the time and money effort is pretty low, and as wider the project gets, as more effort is it to change something. So, and when you start a new high-speed design, what will be your approach? Yeah? Do you have enough experience? Do you have enough competence? Do you just go trial and error, make a prototype, measure it, make another prototype, measure it, or do you go the way of simulate before fabricate? There is no clear yes and no answer to that, but I want to show you a few points where we can help you, because the very important point is, as more you invest in this area, maybe it's annoying, maybe it takes days, even a week to make a simulation beforehand. But the important thing is, if you invest more here and you can go with a, now don't understand me wrong, but a cheaper material, then you save here in this area. Yeah, this is a one-time investment. You invest here one time more time, but you can save here with every produced PCBs in a big range. How can we support you in this area? In the plan phase, we can provide you an impedance controlled stack-up to get the starting parameters fixed. In the design phase afterwards, we can give you design parameters and guidelines. Or if you have not enough experience or no time for this, we can also provide you the design as a service by our Würth Elektronik design team. Just contact us if you need here more input. After the design is done, in the pre-production, we can do a feasibility and design rule check. We have an engineering query process with a documentation. If everything we think suspicious or not clear, we will ask you back and provide you solutions how to fix that problem. In the production itself, we can do special quality control, AOI measurements, or even single track measurements in the production. And sometimes a design in is necessary. And at the end, after production, we can do an impedance control measurement if needed on every production panel. So additional points, we have qualified fully the Panasonic Magnetron 6 material with all available prepregs and core styles. If you need different materials, we can offer more through our Würth Elektronik Asia production team with global sourcing capabilities. We can measure you the material and layout parameters either by the standard impedance meters or with a new Atlas measurement system up to 40 gigahertz. We have a lot of experience by creating impedance controlled stack-ups. We have more than 20 years of experience. And the final last words, high-speed designs can be complex. As earlier we start the discussion together, we can find an optimal solution.